Alright, so in this video I'm gonna be explaining another important paper with the title Graph Rewiring and Preprocessing for Graph Neural Networks based on Effective Resistance. You know, in computer science departments like in University of Washington, where they work very classically and very deeply about graphs, not from the perspective of learning maybe, but from very deep graph theoretical perspective, and they focus on, for example, on the effective resistance and other deep ideas in graph theory. But this paper uses this idea of effective resistance for graph neural networks and graph rewiring. This paper in 2024. Graph neural networks are powerful. However, existing GNNs can generally suffer from two limitations: over-smoothing, over-squashing, and of course many more. And to overcome these issues simultaneously by utilizing the concept of effective resistances, this is good, but calculating this in practice is computationally expensive still, because the A inverse is anything to do with inverse of a matrix is computationally expensive. Anything to do with solving linear system of equations still takes time, and this adds to the computational complexity of graph neural networks, but it has very important topological aspects. First, we do pre-processing by rewiring like this, and then for training tests we do feature embedding, and so finally we remove edges with minimum resistance and add edges with maximal resistance. So the effective resistance between two nodes equals the difference in voltage of these two nodes when the current flow passes from one node to the other is 1 in ampere. And so this is the message passing mechanism that you are familiar with. And graph neural networks has problem of over smoothing because the difference in features between pairs tends to be 0. And similarly, over squashing happens in graph neural networks. But what is effective resistance? Let U and V be a pair of nodes, U and this V. We compute the effective resistance like this. But L is the pseudo-inverse. So calculating is very expensive, but there are several approximation algorithms. Like this paper, they use 3C algorithm. And there is a connection between effective resistance and over smoothing that they explain here. Also, there is a connection between effective resistance and over squashing. They explain it in this theorem. But the global issue of over smoothing and over squashing in graphs stems from local structural imbalances. Here they define this for a graph G with modifiable edge set E, with at most n sub d edges to be removed and n sub a edges to be added. Minimizing the total constraint resistance can be formulated like this. So we propose topological redundancy coefficient and bottleneck sparsity coefficient to guide deletion and addition of edges to improve the convergence rate of optimization function. So the topological redundancy coefficient is this. And we add edges between nodes with minimal bottleneck sparsity coefficients. So the algorithm, first it needs a graph, then we compute the effective resistance matrix. Once we have this matrix R, then we compute topological redundancy vector and bottleneck sparsity coefficient vector. Then we find nodes with maximal topological redundancy coefficient and n sub d edges. Then we remove edges from G that bit minimize R sub G. And we also add edges. So here we add edges, here we remove edges. We add edges with maximize of R sub G of U and V. And we do it for all edges and nodes. So you see the visualization of nodes with redundant connections and graph bottlenecks. And they did experiments for these data sets like Reddit, Mutalk, enzymes, Colab, proteins, and for different, for example, graph convolutional neural networks and the graph sage. These are the baseline, and then they see what happens for different data sets like Wisconsin, Chameleon is very difficult. Chameleon, because it is a heterophilic, it's not a homophilic graph, it's a heterophilic graph, it's very challenging. So this Chameleon and Squirrel, these two are for heterophilic graphs. It's very challenging. That's why even here we see very low accuracy, very low node classification accuracy.